You know all those vibrant colors in your clothes, in plastics, even in paint? They make our world look amazing, right? But a lot of them come with a hidden and potentially pretty dangerous environmental cost. Today, we're going to dig into the problem with one specific class of dyes and the really ingenious ways scientists are figuring out how to clean up the mess.
And the scale of this problem is, well, it's huge. Get this. Over half of all the synthetic dyes made by industry belong to just one group, azo dyes. They are literally everywhere, which makes them one of the most common industrial colorants on the entire planet.
So what in the world is an azo dye? Well, it all boils down to this one specific chemical structure you see right here, the azo linkage. It's that double bond between two nitrogen atoms, kind of sandwiched between two bigger rings. That little N double bond N, that's the magic ingredient that gives these dyes their brilliant colors. But, as we're about to find out, it's also the source of all the trouble.
Okay, so why is the most common type of dye in the world also one of the most problematic? Let's get into the nitty-gritty of the dangers they pose.
So here's the paradox, right? Azo dyes are designed to be super tough and stable. That's what makes them so good for coloring our clothes. They don't fade. But that exact quality, their toughness, makes them incredibly hard to break down in the environment. During the manufacturing process, a whole bunch of it just washes out into the wastewater, and a pretty big chunk of that sails right through our treatment plants and ends up in our rivers and soil. And this is where things get really nasty. So when these dyes settle down in places without much oxygen, think the mud at the bottom of a river, certain kinds of bacteria get to work. But they don't destroy the dye in a good way. Instead, they just snap that central azo linkage. And this is the critical part. Breaking that bond releases these things called aromatic amines, and a lot of those are known to be toxic, and some are even potential carcinogens.
And look, this isn't just a hunch. The research we're diving into, from a dissertation by J.T. Spadaro, spells it out very clearly. The science is pretty settled on this. That breakdown without oxygen, the anaerobic breakdown, is the main way these really harmful compounds get formed. It's a chemical switch from a colorful problem to a serious health risk. Which, of course, brings us to the million-dollar question that's driving all this research. If breaking them down without oxygen is dangerous, is there a way we can destroy them in an oxygen-rich environment before they ever have a chance to turn toxic?
Well, the first answer comes from a place you would probably never ever guess. It's not some new chemical or a complicated machine, but a humble little organism you can find in nature.
So what is this hero? It's a life form that has literally spent millions of years evolving to break down some of the absolute toughest materials on Earth.
I'd like you to meet Phanerochiate chrysosporium. Yeah, I know, it's a mouthful, but it's just a common white rot fungus. You know, the kind of thing you might see growing on a decaying log in the woods. This little guy is an absolute master of decomposition, and scientists started to wonder, could we repurpose its natural talent? And here's the brilliant connection they made. See, this fungus's day job is to break down lignin. Lignin is this incredibly tough, complex stuff that gives wood its strength and structure. So the researchers thought, hey, what if the same powerful, all-purpose machinery it uses to chew through wood could also destroy these stubborn, man-made dye molecules?
And the results? They were really impressive. The research showed that this fungus could completely mineralize up to 38.3% of a dye called disperse yellow 3. And mineralize is the magic word here. It means the fungus didn't just break the dye into smaller, less harmful bits, it broke it all the way down to basic carbon dioxide. Poof, gone.
Okay, so how does it actually do that? What's the secret to this amazing biological cleanup? Let's zoom in on the microscopic action. So the fungus doesn't actually eat the dye. Instead, it just pumps out these really powerful enzymes called peroxidases into its surroundings. The best way to think of them is like tiny molecular scissors. The process is so powerful and just indiscriminate that it's sometimes called enzymatic combustion. These little scissors just go around snipping apart any complex molecules they bump into, and that includes our azo dyes.
Now, what's so cool is that unlike those dangerous bacteria, these enzymes don't attack that central azo bond first. Nope, they go for one of the big side rings first. And that initial attack makes the whole molecule unstable, which then causes that central bond to break apart safely through a totally different chemical process, one that doesn't create those nasty carcinogens. It's just a much smarter and way safer way to get the job done.
But, biology isn't the only game in town. The researchers also looked into a purely chemical approach that works just as well, but in a completely different way.
So if the fungus uses precise molecular scissors This next method, it's more like a molecular blowtorch. We're talking brute force. This is called an advanced oxidation process. And the whole goal here is to create one of the most reactive chemical things known to science, the hydroxyl radical. These things are unbelievably powerful. They will attack almost any organic molecule they touch, ripping it to shreds almost instantly. It's basically a chemical sledgehammer.
And the data here really speaks for itself. For that same dye, disperse yellow 3, this method mineralized over 50% of it, even more than the fungus. And for other dyes, the rates were also incredibly high. It's a fast, powerful, and really effective way to just completely obliterate these pollutants.
So what does this all mean? We've got two very different but very effective solutions to the exact same problem. So let's kind of zoom out and look at the big picture for the future of cleanup. What this research really gives us is a toolkit. On one hand, you've got the biological approach, right? We're harnessing the precise, elegant machinery of a fungus, its nature's solution. And on the other hand, you've got the brute force chemical approach, a super fast-acting and powerful way to just destroy waste. Both of them have a role to play in fighting pollution.
So the main thing to take away from all this is that azo dyes are a massive environmental problem because of how they break down under the wrong conditions. But this research shows us there are safer, oxygen-rich ways forward. Whether we use nature's enzymes or powerful chemistry, the absolute key is to attack the dye molecule in a way that avoids creating toxic stuff. And these ideas, they're not just for dyes. They're powerful tools we could use for a whole range of stubborn pollutants.
And that kind of leaves us with one last thought. The beautiful colors in our world had this hidden danger that we're only just now learning how to clean up. It really makes you wonder, what other invisible pollutants are hiding out in the everyday products we use?